Gauss's law and conductors. Gauss's law can be used to deduce the properties of conductors carrying a net electric charge. An excess charge placed on an isolated conductor moves entirely to the outer surface of the conductor. None of the excess charge is ever found within the body of the conductor itself. So the charge on the interior surface. Now here are three different scenarios. Number one is where the charge resides completely on the outside, right? There's nothing on the inside. Now number two is if the charge is outside and it is hollow. What happens in that case? And number three is when the charge is outside, plus and minus, and you place another charge, which is, say, I don't know, like let's say a positive charge inside. What will happen in each of these scenarios? In order to understand that, what we will have to understand is that the net charge will always be placed on the inside. Solution to this problem lies in the fact that electric field inside the conductor is always going to be zero. So if we place our Gaussian surface inside the conductor, it will mean that the field inside will be zero. So for example, let's say we put a Gaussian surface right here, right? What will happen? There will be no flux. There's no charge inside, so there's no flux, and hence there was no electric field. What about if our Gaussian surface is here? Well, when our Gaussian surface is here, there is still no Q inside. There's no Q enclosed inside, so that means electric field will be zero. Now what about in this scenario? Well, this is plus, so in fact this will be minus. This will start to become a minus, and there's a plus charge in here. Now in this case, it's going to be very interesting because to the outside, if you were to look at this Gaussian surface won't even recognize that this conductor is there. To the outside world, it will just look like that there is one single charge that's placed inside. What about a scenario like this? A negative charge in a neutral conducting metal shell. So if you were to place a negative charge here, and then this would be just a conducting metal shell that surrounds it. What will happen? If you were to place your Gaussian surface here, this negative charge will induce a positive charge here, which induces a negative charge here, and to the outside world or to the Gaussian surface, it will only appear like there is only a 1 minus charge there. And to the outside world, it will just appear like there's a sink there and there's nothing else. Now what about electric field in and around conductor? Electric field just outside a conductor will have a magnitude sigma over epsilon naught, and it will always be directed perpendicular to the surface. So in order to calculate what the E will be like, how did we calculate this? We drew a small pillbox that extends outwards. So again, there is no field around the surfaces. The only field is around the two sides. And in this case, it'll be only in one side because we're going to be considering one side E will be equal to absolutely zero. One side is inside the field and one side is out. In this case, it'll be E dot A, only one surface, Q over epsilon naught, or sigma A over epsilon naught. So E field will equal sigma over epsilon naught. Now let's do an example. Figure A shows two portions of two large sheets of charge with uniform surface charge densities of sigma plus and sigma minus, which is equal to minus 4.3 meters squared. Find the electric field due to the left of the sheets, in between the sheets, and to the right of the sheets. Okay, so now let's do this problem. So there are two sheets. One has plus charge on it. One has minus charge on it, and it says sigma plus and sigma minus, which are given. This is to be about 6.8 microcoulomb per meter squared, and this is minus 4.3 microcoulombs per meter squared. Okay, so these are the numerical values of my sigmas. Okay, and what it's saying is that you have to find E field to the left, E field in the center, and E field to the right. So these are the three fields that I am looking for. Okay, so how do I solve this problem? First of all, I'm going to employ a strategy. First of all, I'm going to look at these sheets separately. So this is a plus sheet. So it is going to have fields that look like this, and these fields are also going to be present here, right? So this E field is going to continue all the way through. The the right-hand side is a negative field, right? So in this case, the field will be pointing inwards from both sides, right? And again, on this side also, because of this, it is going to be pointing inwards, right? So these are my two fields that I have. Before I begin, let me just find the electric field due to the plus, and I used a green one, so I'm just going to use E plus. It is going to be sigma plus over 2 epsilon naught. Plug in the values, I get 3.84 times 10 to the 5 newtons per coulomb. It's just literally just plugging them in. And my E minus is going to be sigma minus over 2 epsilon naught, which gives me minus 2.43 times 10 to the 5 newtons per coulomb. Okay, once that is done, now comes the job of figuring out what happens on the left side, the middle, and on the right side. So I'm just going to erase this for now, and I'm just going to write them here. So E to the left. What happens to E to the left? EL will be, well, this, if I choose this as my positive axis in this, then this would give me my negative. So E plus, in this case, will be minus E plus. Why? Because it's pointing towards the negative side. And E minus will be plus towards the left side. Do you see it? It's pointing towards the plus, and that's pointing towards the minus. Okay? E center will be what? Both of them are pointing towards the right, so they are both plus. Then what happens to E on the right? Well, in this case, my plus field is plus and my minus field is minus. Do you see how that worked out? And then all that's left is for me to plug in these values at these certain points and to calculate. And I believe my answers come out to be minus 1.4 times 10 to the 5 newtons per coulomb. But please make sure that you check that. E at the center will be 6.3 times 10 to the 5. And E to the right will be 1.41 times 10 to the 5. So, where do each of these point? Well, this points towards the negative direction. So it points left. This is positive, so this points to the positive direction, so this is pointing to right. And this also points positively, so this is also pointing right. So these are my 3 E's. Example 2. The electric field just above the surface of the charge drum of a photocopying machine has a magnitude E of 2.3 times 10 to the 5 newtons per coulomb. What is the surface charge density of the drum if it is a conductor? Well, this one is pretty straightforward. So it's asking me for the surface charge density. I know that the surface charge density is equals to epsilon naught E. I know epsilon naught is 8.8 times 10 to the minus 12 coulomb squared over Newton meter squared. And E will be 2.3 times 10 to the 5 newtons per coulomb. Okay? You multiply them together and you get 2 microcoulomb per meter squared. So that was a pretty simple example.